Hi, in this video we'll discuss about dual form of SVMs. So in our last video, the optimization problem we arrived at is a constraint optimization problem, and it is called as a primal form of SVMs. So if we apply our Lagrange multipliers to the primal form, it becomes the dual form of SVM. So our primal form of SVM is, let me rewrite that equation. Primal form for hard margin SVMs is uh, find the minimum value. We have to minimize for some values of W and B. We have to minimize this part. That is our hard margin SVM or the primal form. Now, before going into the dual form, I'll explain you what is a Lagrange multiplier. Lagrangian multiplier. Lagrangian multiplier. So what? Uh, before even going to Lagrangian multiplier, the primal form of an SVM has a constraint, which is yi into w transpose xi plus b should be greater than or equals to 1, and this can be written as yi into w transpose xi plus b minus 1 should be greater than or equals 0. So this is a constraint optimization problem. Now what Lagrange multiplier does is, if we have a function f of x and has a constraint, that f of x has a constraint g of x, then what Lagrange multiplier does is it tries to find a local maxima and minima for function f of x, and it can be represented as Lagrange multiplier of for f of x is f of x minus lambda times g of x. So here g of x is the constraint for function f of x, and our lambda is over here is the hyperparameter. And uh, so writing the using this concept, where is my cursor? Yeah, using this concept for Lagrange multipliers, we'll write the equation for our constraint optimization problem, and it becomes Lagrange multiplier for some values of w and b. All I have to do is argmin of find the minimum values for this part minus alpha times constraint equation. So for this, the constraint equation is this part. So let me rewrite that in a new notepad. Yeah. So expanding this equation, this becomes, oops, now this part becomes argmin find w and b for which we can minimize the inside part, w transpose w by 2 and summation of I equals to 1 to n alpha I and my constraint yi w transpose xi plus b minus 1. Now, and for this, my alpha I should be greater than or equals to 0. Now, sorry, getting the gradients for my Lagrangian multiplier with respect to W and D, this becomes, we know gradient, right? It's taking derivative of L with W. And so this becomes, if we take the derivative for this part, it becomes W minus I equals to 1 to N alpha I yi xi equals to 0, which implies W equals to alpha I yi xi summation over I equals to 1 to n. And similarly, my Lagrange derivative for Lagrange with respect to b is, we don't have b term, so this part is 0, and this part will be 0, and yib and alpha I. So this is summation of I equals to 1 to n alpha I yi equals to 0. Now let this be 1, 2. I'll tell you, we will use these equations for for doing the further derivation. Now our original equation becomes now, yeah, our original equation becomes is like this part. We can substitute equation 1 and 2 in this part. Now it becomes 1 by 2 for summation I equals to 1 to n. We know W is alpha y xi, right? We'll be using here is alpha I yi xi whole square minus summation of I equals to 1 to n alpha I yi, and my W is again summation of I equals to 1 to n, or j we used I here, so j equals to 1 to n alpha j yj xj. So this is my W, right? Now this multiplies with xi, and then plus b yi w and minus 1. Let me check the equation. yi w transpose xi plus b minus 1. Right. Now this, now again we can expand this equation. Let me maximize this. Now we can expand this equation further. Half of summation of I equals to 1 to n, and it's alpha I yi xi alpha j yj xj minus, now inside part we can multiply, and this becomes I equals to 1 to n summation j equals to 1 to n alpha I alpha j yi yj xi xj. Xi gets multiplied, right? Minus b times of summation of I equals to 1 to n, like this part and this part, I equals to 1 to n alpha I yi plus this part and this part, summation I equals to 1 to n alpha I. When we solve this equation, finally we'll arrive at summation I equals to 1 to n alpha I minus, we have a half and minus 1, so it becomes minus half I equals to 1 to n, j equals to 1 to n, alpha I, alpha j, yi, yj, xi transpose xj. And this equation is valid such that my alpha I should be greater than or equals to 0, and summation I equals to 1 to n alpha I yi should be equals to 0. For these constraints, for these conditions or constraints, this equation is valid. And if you can think, this is a representation of my linear SVM. And one important aspect of a dual form is this part can be kernelized. So instead of writing xi transpose xij, if I write it as k into xi xj, then becomes a kernel form of an SVM. Why kernelization is important is, like, if the points are linearly separable, like if I have my data points, like set of positive classes here and set of negative points here, I can find a hyperplane which can classify these points to their respective classes. So for this, linear SVM is sufficient, right? And what if I have my data points represented like this, and like, so this is not linearly separable, right? So linear SVM in this case is not valid. So, and we also learned in our logistic regression, if if f1 and f2, like this data is distributed between f1 and f2 features, then when we transform it to f1 square and f2 square, this can be converted to a linear form, like linearly separable form, right? So in that case, we can apply our logistic regression or linear SVM. But what my kernel SVM does is, it internally takes care of transformation. Takes care of transformation. Like the transformation is being applied here, that will be taken care internally. So that is the important feature of the main distinct feature of our kernel SVMs. Kernel SVMs, which essentially means this part can be replaced by anything. This could be represented as a polynomial kernel or an quadruple kernel, depending on which works well, which fits the, like here it can be a polynomial kernel, like a quadratic equation, right?